Our next type of nonlinear models are designed to deal with finding optimal locations for a small number of warehouse facilities with respect to much large number of customers buying products that are shipped from those facilities. The quadratic distance function is used to approximate the quote-unquote cost of satisfying customer demand from a particular facility, and this makes the situation a nonlinear programming problem. We will start and end with a single warehouse and only 4 customers, right? But a more complicated, more general problem, would involve multiple warehouse facilities as shown in this graph and hundreds or thousands of customers. So in this problem, it is not as much a question of how much to ship from a given facility to a customer destination site as it was in the transportation problem we discussed in the previous chapter, one of the previous chapters, but rather where to locate the facilities in the first place so that the cost of future shipments can be minimized. The actual forecasted demand, or these shipments, is a huge factor in these models and is typically used as a weight imposed on these geographical distances from the proposed sites. The model typically starts with a single facility, as ours will, and then expands to multiple locations to compare the distance savings derived from using several facilities, etc., etc. In a more complex version, we will not do. Okay, so what we'll do right now is to find the optimal solution for a single warehouse so that the total straight line distance from each of the customers is minimized. This will allow us to learn about the basic form of the model and visualize the result on the chart shown here in the bottom right corner of the screen. And again, notice that the distance function, right, is the standard Euclidean straight line distance is the square root of the difference between the x coordinates of 2 points, right, x1 minus x2 or x2 minus x1 squared, right, where the c represents customer, w warehouse, plus the same thing for the y coordinate. Okay, a brief review. So let's open up the Lexix location model right here and briefly review the annual shipments here that will act as the weights as well as the actual coordinates shown here. Customer 1, for example, is 510, this guy here, right? And so for the other customers are located at these other few points, right? So a brief review of these shipments, right, will show what seem to indicate, because of the highest number next to customer 4, pretty high number of shipments to customer 3, that somewhere here, towards the bottom right corner would be the optimal location, right? Perhaps something like 8, 4 or 8, 5 or 8, 3, somewhere around here. So I'm going to type 8, 3. I could have used any other, and it's going to pop in the warehouse, proposed warehouse location, so I have something to work with, right? Then using the formula I was just showing here, right, for the distance, straight line distance between 2 points, okay, we're going to calculate the straight line distances in column F from each of these customers to the warehouse. So straight line here to here, straight line here to here, here to here, as well as here to here, right? Again, the CX and CY are the coordinates of customer locations, like 510 here, okay, whereas the WX and WY are those for the warehouse, the A3 currently, right? Okay, so to calculate that, we need a square root, right, of the difference in parentheses between the customer x coordinate minus the warehouse x coordinate, where the warehouse has to be clearly fixed, and that's squared, plus the same thing for the y coordinate. Okay, again, don't forget to lock the coordinates of the warehouse. Okay, then close the square root function and you're going to get a number. Okay, you apply that same formula for the other ones, and then for the annual distance, or total distance I should say, right, we use those annual shipments as weights on these geographical distances. So it is simply going to be a sum product of those annual shipments acting as weights with these straight line distances in column F. And for this initial solution, we should get 5,856 weighted miles, right? Or whatever. Okay, so the total distance then, this number, we're hoping they can minimize it by changing the location of the warehouse, okay? Without any constraint other than the non-negativity one. So the solver setup is extremely simple here, right? We click on the objective, add this cell F13 to be minimized by changing by changing the XY coordinates um, and assuming that the whole, of course, they're going to be non-negative. We could constrain them to be between, obviously, something like 0 and 15. We can constrain the space, but in this case, it doesn't really matter. Again, because the Euclidean distance equation, this guy, where are you here, right, is a smooth, function, right? It's a smooth function. We can use the standard LSGRG nonlinear model, and it's going to find the solution pretty quickly by improving the this weighted distance by about 400 units, right? 400 distance units, and it will actually place the location very close to that customer number 3, right? Or 2, I should say, customer number 2. Customer number 2 right here, okay? And for the total distance, right? So at the location 9.3, about 5, right? So that should do it for the location model. And switch back to the presentation and pause.